Hello everyone. I welcome you to this channel, and this session, this lecture is going to cover almost all the basic terminologies and the concepts associated with quantum computing. So this will be very important for you, and if you have any doubt after this lecture, then the comment section is open for you so that we'll have a better interactive session. We'll have a better discussion on these topics. So you are with Dr. Dipajyoti Bora. Let's start the class. What is quantum computer? A quantum computer is a machine that performs calculations based on the laws of quantum mechanics, which is the behavior of particles at the subatomic level. So remember here, what term is mentioned is the subatomic level. So this particular theory, this particular concept, quantum mechanics, is the base on which today we have the quantum computing field is being developed to a great level, right? Now, how exactly the quantum computing is different or differs from our traditional computing? That is the main point of discussion here, right? Now, quantum computer that relies on special memory known as quantum bit to perform massively parallel computing. So you just got the answer. So first term I told you that subatomic level, not atomic level. Here we are specifying subatomic level. Second thing I just told you that the bit here refers as quantum bit, which is the special memory, because quantum bit is the main reason by which a quantum computer differs from a traditional computer, where we used to deal with bit that is 0 or 1 values, right? But here quantum bit, and how we define quantum bit we'll discuss. But this quantum bit helps quantum computing to perform massively parallel computing. Now you can see here this particular machine here, right? A depiction of quantum computers. So this image courtesy means right is by Justin Fantel. No matter. So just look at this picture. Now, how or what do you mean by quantum? How you define quantum, or what do you mean by quantum? In physics, a quantum is the minimum amount of any physical entity, that is physical property, involved in an interaction. That is the physics part, that quantum is the minimum amount of any physical entity, physical property involved in an interaction. The fundamental notion that a physical property can be quantized is referred as the hypothesis of quantization, which means that the magnitude of the physical property can take on only discrete values consisting of integer multiples of one quantum. So any physical property can take discrete values, and these discrete values are the integer multiples of one quantum. Suppose a photon is a single quantum of light or any other form of electromagnetic radiation. Similarly, the energy of an electron bound within an atom is quantized and can exist only in certain discrete values. So for us, this photon you can consider as a single quantum. Similarly, this electron bound within an atom, this can be considered. So these are some examples of quantum. Now let's have a look on some history part also. I think I can safely say that nobody understands quantum mechanics, that is by Feynman. Well, he is the research Feynman. Now, why he says like that? Research Phillips Feynman. Now, he was an American. Actually, he was this Richard Phillips. He was an American theoretical physicist known for his work in the path integral formulation of quantum mechanics, the theory of quantum electrodynamics, the physics of the superfluidity of supercooled liquid helium, as well as his work in particle physics, for which he proposed the Parton model. Well, this is his introduction, but he is exactly famous for this quantum mechanics. For contribution to the development of quantum electrodynamics, Feynman received the Nobel Prize in Physics in 1965, jointly with Julian Schwanziger and uh, Tomong Naga. Okay, sorry for my pronunciation. So, but basic thing that you have to remember that Feynman is associated with quantum computing. You may sometime you may face a question or an MCQ like this, because we have to know that who actually introduces this concept. Now, in 1982, Feynman proposed the idea of creating machines based on the laws of quantum mechanics instead of the laws of classical physics. Then again, some more development like 1985, David Deutsch developed the quantum Turing machine, showing that quantum circuits are universal. Then in 1994, Peter Shor came up with a quantum algorithm to factor very large number in polynomial time. Okay. Then in 1997, this one is very important. Okay, please remember, Love Grover developed a quantum search algorithm which big O of root over n means square root n complexity. So why this is important? Because this algorithm you will face in this quantum computing paper. And in recent days, IBM has been one among the top tech giants who is providing quantum services. Now, this is a little introduction of what is quantum mechanics and who introduced this and how it differs from traditional computing. Right. Now, let's have a question for you. Please don't forget to answer the questions by comment. In that way, we can make our lectures interactive, because I am here in a different location from virtually we are interacting, right? So you have to answer me the questions I am asking here. So what do you mean by quantum? Write the answer here in the comment section. Then state true or false. Grover's algorithm is a quantum algorithm for searching an unsorted database of n entries in big O of square root n time. So you can answer like question 1, answer, question 2, answer. Okay, so now Charles Turing thesis. Charles Turing thesis states that a computational function can be solved using any computational device if and only if it is computable by a simple machine called as Turing machine. So Turing machine, we know it was named after Alan Turing, right? Now this Charles Turing thesis says that any computational function, actually, why we need computer? To perform some operations. And to perform some operation, what we need exactly? We need some equations, right? We need some equations so that we can solve that equation and we can get the answer. So for any computational function, it can be solved using any computational device, even only if it is computable or it is recognized by Turing machine. Charles Turing thesis. So in 1936, Alonzo Charles created a method for defining functions called this lambda calculus, where he defined an encoding of the natural numbers called Charles numerals. I think this part you have got in your engineering mathematics, right? So then in 1936, before learning of Charles' work, Alan Turing created a theoretical model for machines now that is known as Turing machine that could carry out calculation from inputs by manipulating symbols on tape. So one was Alonzo Charles, because of which this lambda calculus been created, and where he defined encoding of natural numbers, and they've been named, those natural numbers being named as Charles numerals, right? And in 1936, Alan Turing created his Turing machine. Now, Turing machine, let's have a look on this. Alan Turing created this model for computing general purpose, general purpose computers performance or operations. Now, it is consisting of this, where M is the Turing machine. Now, Q is the finite set of states, right? And then uh, this is a finite set of external symbols. Then this summation is a finite set of input symbols. Then B stands for what we already know, blank symbol majorly used as N marker for input. Then this is a function known as transition or mapping function. Now, Turing thesis, you got it. This thesis concerns an effective or mechanical method in logic and mathematics. A method M will be known as effective, will be called effective or mechanical, just in case M is set out in terms of a finite number of exact instructions, each instruction being expressed by means of a finite number of symbols. M will, if carried out without error, always produce the desired result in a finite number of steps. So that's what the Church-Turing thesis provides. So this Turing machine is directly associated with the Turing thesis. So according to Turing thesis, M will be called effective or mechanical only when M is fulfilling this Turing machine conditions. You can shortly say like that. Clear? Now, classification of Church-Turing thesis. This Church-Turing thesis can be classified into normal Church-Turing thesis and strong Church-Turing thesis. Now, the classical strong Church-Turing thesis says that a probabilistic Turing machine can efficiently simulate any realistic model of computation. Classical strong Church-Turing thesis has a disadvantage that it is not so efficient to simulate any quantum device. Therefore, the quantum version of this thesis, the quantum version of this classical strong Church-Turing thesis has been introduced, where the probabilistic Turing machine can be replaced by a quantum Turing machine. Okay. Now let's come to the main part. So after clear these two facts, very important facts, Church-Turing thesis, where a machine will be called effective or mechanical only when it is satisfying the condition of this Turing machines. Condition means that it can means execute this finite number of exact instructions and they can be carried without error. Right. Now, again, we divide the Turing thesis into normal and strong one, and strong one is okay, but if it is if it is the case of quantum device, then it is not so efficient. So we again have a quantum Turing machine out of this particular classical strong Church-Turing thesis. Now let's come to the main part, that is qubit. What is qubit? I told you that quantum computers differs from traditional computers by this particular storage capacity, by this particular qubits. Well, this is classical bit. You can see here, classical bit. Classical bit can be either 0 or 1 at a time. Got it? Either 0 or, suppose you in your room, you just switch on your fan or switch off your fan, right? Either 1 or 0, but it cannot be in between them. Yes, got it? Now let's come to the qubit. The qubit, here you can see the how we are representing this. See, look at this and look at this. Now, in this case, any combination of them is possible, any combination, right? So this is a kind of more powerful, and at the same time, it can offer more massive parallel computing if we compare it with our classical bit. So qubit in that case becomes more powerful. So as we are considering any superposition of these two, right? So, but you have to represent qubit like this. I hope it is clear to you. Okay, let me clear the drawings. Okay. Now, what is a quantum bit or qubit? A basic unit of memory that uses superposition of quantum effect to store information. So qubit or quantum bit is the basic unit of memory, like we call now bit, then we call byte, then kilobits or kilobytes, like that, right? Gigabytes. So now here the basic unit is qubit. And this basic unit of memory uses superposition of quantum effect, and that is known as entanglement. Remember this term. So what is entanglement? Superposition of quantum effect. So actually it is a kind of mixing, right? So superposition of quantum effect, entanglement to store information. So a qubit stores the probability of information. It represents both 1 and 0 at the same time. So you now got it that how qubit has the power or differs from the classical bit, because qubit stores the probability of information which can and it can represent both 1 and 0 at the same time. Not our case of traditional computing, what we are using here, 0 or 1, either one of them possible, right, at a time. But here, both can be possible. Well, okay, let me explain this. Now, a bit of data is represented by a single atom that is in one of the two states denoted by these two. Now, I told you now, these symbols, remember, you have to write this. You have to write like this. Now, a single bit of this information is known as qubit. A bit of data represented by a single atom that is in of two states denoted by either this or this. Now, a single bit of this is known as qubit. Okay. Let me clear this. Now, a detailed diagrammatic explanation. Now, image credits thanks to Joseph Stelmach. Now, you see here, this is, this is state 0. This is state 1. So, in case of here, means when we talk about the nucleus and different states, so excited state is there, ground state is there, and electron. Light pulse of frequency lambda for time interval 8t. Now, from this ground state it moves to excited state, but it directly does not jump, actually doesn't jump. So it goes through a kind of superposition. So from ground state to excited state. Now this is state 0 at the ground state. Now it comes to the excited state. So this is state 1. Because how this happens, light pulse of this frequency at the for interval t happens. Because of that, this state changes from state 0 to state 1. Now, superposition. You have seen that I have used a term, means just in the last few slides, that superposition. What is superposition? A single qubit can be forced into a superposition of the two states denoted by the additions of the state vectors. So you can see here 0 and 1, these two states, right? With the help of alpha 1 and alpha 2, we can have a combination of them. And this alpha 1 and alpha 2, these are some complex numbers, so that alpha 1 square, alpha 2 square is equal to. So this particular combination, we call it as a superposition. Now, a qubit in superposition is in both of the states, this 0 and 1. For your information, I'm calling it as 0 and 1 so that you don't get confused. But these are exactly not our traditional 0, 1. This is the quantum bits, right? So you have seen that due to this superposition, due to this particular superposition, any quantum bit can be means in either of, or you can say in both of these two states at the same time, because this state is a combination of both of them now. So that's why. And remember, these values, alpha values, they are actually complex number and they are satisfying this particular equation. Kindly note down this. Let me clear the drawing. Okay. Well, now let's again come back to the main question that may be asked in any interview or any exam. What is the difference between bit and qubit? The key difference between these two lies in the ability of a quantum state to represent many possible classical states at the same time. Thus, you have seen that because of the superposition, this 0 and 1, it's different combination. Because if you take alpha 1, alpha 2 values different, then you can have a different combination, different values, right? So because of that, any combination is possible. Now, classical bit, but in this case is a little bit what? it can either be 0 or 1. It cannot be a combination of two. But a quantum bit is instead any possible combination or superposition of 0 and 1 with complex number as coefficients of the superposition. That is, where a bit of information in a classical computer can be represented by 2.0 or 1, a qubit in a quantum computer is instead represented as any point on the surface of a 3D sphere known as Bloch sphere. This is the Bloch sphere I'm talking about, right? This is quantum 0, this is quantum 1. I told you about the ground state and excited state. Now, any combination of them is possible. So qubit is, it can appear in this particular sphere, and this sphere, we call it as a Bloch sphere. Okay, this is a 3D sphere. Well, let me again clear this. Okay. I'm clearing this one. Oh. Not only can is qubit be in such a superposition state, but the system as a whole can be in a superposition of every combination of different states of all the qubits. Because see, a system is built up of different qubits, and each qubit is a combination of others. So as a whole, we can say that the whole system can be superposition of any combination of different states of those different qubits. That is why a quantum computing could be so immensely powerful that every possible state could be stored and processed in a parallel with all the others. So that's where exactly the power of quantum computing lies. Main reason, any combination, any superposition of different qubits are possible. And again, qubit itself is a superposition of any number of states, 0, 1, and that is where we are taking the complex number as coefficient. Now, because of this, any parallel computing, any massive parallel computing is possible, and that's how the quantum computing is more powerful than our traditional computing. Now, the number of possible states that can be present in a supercomputation is huge. If you have n qubits, then there are 2 to the power n possible states in the superposition. Remember, I'm keeping it in red bold so that you should not forget about it. Write down, right? So imagine a quantum computer with just 30 qubits. Then how many possible states we may have? This big number. Of course, you can see here, you can count here. I'm not going to count it for you. You can count. So I mean to say that only just for 30 qubits, you may have this number of possible sets. So imagine a quantum computer with a 300 qubits that would have roughly the same number of possible sets as the total number of atoms in the known universe, in our universe, right? So bits, classical computer, operations 0, 1, on, off, quantum bits or qubits, quantum computers, operations like 0 and 1 at the same time, so superposition. So qubits can take same value simultaneously. This characteristics expands the possibility of parallel calculations. Now let's come to today's question. State how qubit differs from bit. Don't forget to write the answer. I know that question maybe seeming to some kind of easy, but you should not skip this. So first question means for this question will be question number 3 in this lecture because I'm covering all the basic points here. So question number 3 says that how qubits differs from bit. Then question number 4, state true or false. If we have n qubits, then there are 2 to the power n possible states in the superpositions. Yes or no, true or false. Write down your answer. Well, the power of quantum computation and PQP. So this P, I hope you know P and PT's problems, right? Now, this is BQP. See, this is P, this is NP. Now, BQP lies somewhere like this in between of them. And this is as a whole P space. So problems that may take classical computers thousands of years to solve, quantum computers can solve with just a second. Right. Now, I hope then up to now you got it that how it can solve because of the parallel computation, because of the power that every states can be possibly means involving 0, 1 at the same time with different superpositions. So problems from data encryption, inventing new drugs to creating more precise climate models, everywhere we can use this. So reasons behind the power of quantum computing, first of all, superposition, second of all, entanglement, third of your interference. Superposition, you got it, right? Entanglement means I am talking about that particular effect. Interference means it can parallelly exhibit everything. So obviously that that actually possess some kind of more power with respect to this interference. BQP, what is that? In a computational complexity theory, bounded error quantum polynomial time. Remember, bounded error quantum polynomial time, shortly we call it as BQP, is a class of decision problems solvable by a quantum computer in polynomial time with an error probability of at the most of 1 by t of all instances. It is the quantum analog to the complexity class BPP. So remember, just to think, BQP stands for bounded error quantum polynomial time. Here, what happens exactly, we deal with some decision problems that is solvable by quantum computer in polynomial time and with an error probability of 1 by t of all instances. Now, what is BPP? BPP. In a computational complexity theory, bounded error probabilistic polynomial time. Remember, bounded error probabilistic polynomial time, BPP, is the class of decision problems solvable by a probabilistic Turing machine in polynomial time. So BPP is the class of polynomial, or you can say decision problems solvable by probabilistic Turing machine in polynomial time with an error probability bounded away from 1 by t of all instances. Now, BPP is one of the target practical classes of problems, meaning most problems of interest in BPP have efficient probabilistic algorithms that can be run quickly on real modern machines. BPP contains P, that is the class of problems solvable in polynomial time with a deterministic machine, since a deterministic machine is a special case of probabilistic machines. So if a problem is in BPP, if there is an algorithm for it that has the properties like it is allowed to flip coins and make random decision, it is guaranteed to run in polynomial time because P is involved, right? And on any given run of algorithm, it has the probability of at most 1 by t of giving the wrong answer, whether the answer is yes or no. So we can say a decision problem is a member of PQP if there exists a quantum algorithm, right? Quantum algorithm means an algorithm that runs on a quantum computer that solves the decision problem with high probability and is guaranteed to run in polynomial time. A run of the algorithm will correctly solve the decision problem with a probability of at least 2 by t, at most 1 by t, and at least 2 by t. So we can represent the power of quantum computation like this. This is BQP and this is P. PCP is involved, and this is NP and this is P space. Probable means solving in a polynomial time, not in a probable means polynomial time, and this P space. So here we have our BQP. Okay, so you got it. P in polynomial time solvable, and P verified in means polynomial time, and P space solved in polynomial space. But we know that we already have some problems like this one, whether P is equal to or not equal to NP, and P space is bigger than NP. NP complete is associated with this graph isomorphism. But my suggestion is that you just stick to this particular. Just let me clear this. Okay, just a minute. Just stick to the BQP only, because this thing may be asked that BQP, whether it is including P or not. Yes, it is included there. Well, let's come to question. State what is BQP in reference to quantum computing. State true or false. Integer factorization is a NP complete problem? Yes or no? True or false? Now let's come to again one more important term, that is entanglement. Okay? Well, quantum entanglement is a quantum mechanical phenomenon in which the quantum states of two or more objects have to be described with reference to each other, even though the individual objects may be spatially separated. Repeating again, quantum entanglement. What is that? Is a phenomenon. I told you, no, it's a phenomenon, a kind of, you can say, action where quantum states of two or more objects can be described with reference to each other, right? Suppose Q1, Q2, they can be described with respect to each other, even though the individual means they is may be spatially separated. So this is a physical phenomenon that occurs when a group of particles is generated, interact, or share spatial proximity in a way that the quantum state of each particle of the group cannot be described independently of the state of the others, including when the particles are separated by a large distance. So they are associated to this particular phenomenon, quantum entanglement. Got it? Note down this. So in short, we can say that entanglement is the ability of quantum system to exhibit correlations between states within a superposition. Superposition, you got it? Combination of those different states, right? Bits, qubits. Now, entanglement is the ability of such superposition. Entanglement is the ability of quantum systems to exhibit correlations between different states within a superposition. So look at this picture. I think this picture you can easily see laser beam, crystal, vertically polarized photons, horizontally polarized photons, and these are entanglement photons because they are associated, although they are spatially separated. Imagine two qubits, each in the state this quantum 0, quantum 1, a superposition of 0 and 1 now plus, right? We can entangle the two qubits just that measurement of one qubit is always correlated to the measurement of the other qubit. So we can entangle two qubit so that one qubit is always correlated to the measurement of the other qubit. I hope it is now very clear to you. Superposition, combination, right? That entanglement, the ability of correlations between those different states and the superposition. Let's take one more example. It is possible to prepare two particles in a single quantum state such that when one is observed to be spin up, other one will always be observed to be spin down, like vice versa. This is despite the fact that it is impossible to predict according to quantum mechanics which set of measurement will be observed. As a result, measurements performed on one system seem to be instantaneously influencing the other system entangled with it. Means they are associated, right? One effect on one will obviously impact on the other. Well, so with this, I have covered almost all the facts, means basic facts. I'm not saying that everything I have covered. Like some things left, then that I will cover in some other class. If you want, then you can ask me for that such classes. Like means Gover's algorithm, search algorithm. These things will cover, no doubt. But the basic things that when someone asks you that what is quantum computing, how it works, what are the different sorry powers of it, and all the facts, superposition, entanglement, these things we have covered in a single class. So before exam, at least revise this class, then that will be helpful for you. Either it is an interview or it is your board means university exam, doesn't matter. It will help you. Okay. So with this, I'm ending this session. Dr. Dipo is signing now. Bye-bye. Take care.